You can have to take it. So, good afternoon everybody, thank you for coming, and sorry for being late again. It is out of my responsibility, unfortunately. The Hungarian railways are interesting. So, we will have very interesting topics today. For example, superconductivity. But let's talk about the last lecture. So there were some problems with the slides last time. For example, some Hungarian text remained on the images. And unfortunately I had no time to correct them, but I will do it. So whatever we have, I upload. I also will add some supplementary text to the slides. For better understanding. So the aim is that, and purpose is that, you have to use only the slides and perhaps some book to understand the theoretical approach of this lecture. So this is it. There will be problems also with these slides. So fortunately there is a holiday. And in this holiday, I can do anything. For example, whatever slides. Oh, I have my cross problem. In Hungary, if you travel at trains, you leave the cities, then you have no mobile internet connection because the field is so big. So if you go to a very far city like Százhalombatta, 20 kilometers of Budapest, there is no connection. If nowadays, if you are in the city, you sometimes don't have connection. So I need days to recover and write everything that I need. I uploaded the materials on Moodle, YouTube, GitHub, but I will change the slides very soon. On practice, I will explain you there was some problem with the exercises. It's a long story, and I finished the last exercise. So where we are, last time I didn't talk about thermoelectric phenomena, about the properties of the material, ferroelectricity, piezoelectricity, and electro-stringtian liquid crystals superconducting. The part of liquid crystals will be very weak of my presentation today. I will add additional material for this. Well, for your consideration. Okay, let's talk about Alexander Volta. So the potential is noticed, and the unit of potential is by Volt because of him. It's very interesting. He was an Italian scientist. It is not physics, just science and culture. I always check the name of the different scientists who are very good, and we remember that. First, we started with Galileo Galilei, Giordano Bruno, and other Italians, because at that time when they lived, the center, the economic center of the world was in the Mediterranean. Long time ago, during the ancient Greek times, and later the times of the Arab caliphates and everything, the center was there. But sometimes I mention those guys too. But here, it's interesting, the center was Mediterranean in Italy. Then it moved to France, no, not France. First moved to UK, Newton, and other guys. And then, I just started. And then it moved to Germany, France, and then at the beginning of the 20th century, the center moved to somewhere in the United States. Now the center is somewhere in the Pacific, just you cannot follow, you cannot tell the many Chinese names and other things. But this Volta did. He constructed the first battery. Actually, in the Western civilization, because there were battery, I don't remember exactly, I have to Google, but there was battery in, perhaps in the Sumers. They have something similar stuff. What he had done, he took zinc and different metals and put humid textile between them. So first, I don't know, it's zinc, then other material, then text, other material, and did this, and he constructed a chemical battery. It's the same like we have, just this was the first time. And then, yeah, this is, oh, sorry for the Hungarian text, this is the same. This is Volta's battery. Sorry, I have to check something, because this is a bit broad. Zinc and copper. So that was the two materials that he used. Zinc and copper, and he put humid textile between them. Part of this textile was the humidity was not only water but some salted water. But I don't remember exactly. But it is important. This column, this Volta's column, it's a battery. This is very interesting, and with classical dynamics, you can explain it. You put two different metals together, and then you experience some power, some current, some electricity. This is only just a brief introduction, but I have in my mind two very bad examples for this. In the old days, when I was young, teeth were repaired by amalgam array. And if you do have this feeling in your teeth, not ceramic but amalgam metal, wood? No, you are too young. I have one only. I have old teeth, but one is weird. This age doesn't matter. But it's ceramic. In the old days, it was filled by an amalgam oil. And if you bite a chocolate and the aluminum cover of the chocolate was in your mouth, then you feel electricity and swearing badly. Because what happened? Aluminum, one metal, amalgam in your teeth, other metal. In your mouth, there is some electric stuff, and that's a battery on your nerve in your teeth. That's good feeling. So people then scream. That's a battery. That's the same, like here. Just that's useful, and this amalgam stuff in your teeth is not useful. When you do this, the materials degrade and disappear. It's very, very difficult actually. There are different ions, they are moving. So the material changes. It's called corrosion, and you have exactly the same when you have iron, just normal iron, and water. It's a small battery, and this process chemically destroys the iron. If you have one type of metal and another type of metal, and you have a what is it? Sphere. Sorry, that's awkward. But so you fix somehow them together. Skew. If you have skew from different materials, then you must be extremely careful, because if some things, the potential that I will teach you soon, is not the same, then they start to corrode each other. It's a battery, and also with humidity it forms a battery, and it destroys the metals. Okay? Understandable? Have you ever heard about this? No? Never? You will, don't worry. But this is just a physics part. You have two different material A and B. There is, you put them together, and there is a potential between them, and you can experience electricity. You know this instrument, I guess. But the question always, why? There are two approaches. First, volt potential. There is one metal, other metal, and there is potential between them. There is another stuff, it's galvanic potential. There is potential difference between internal power points of the metal. It's a different approach. But it was in the 18th century, so they had experience, they had what experience? Experiment, and also experience, of course, but they didn't understand what's the problem, what is the reason of this. But against them, you already know these energy level of the metals. So there are, I will translate everything, sorry. There are two different metals, and in one metal you have electron level. There is another metal, and there are also electron level when the electron could have, you know, Faraday statistic and everything. So, but when you touch them, the electrons from the higher energy go to the lower energy. it is in one metal, the other is in the other metal. It means the electrons leaves one metal, so there is a positive. So it's, the charge is missing, so it becomes a little bit positive. The other becomes a little bit negative, minus. So you have a potential difference, and this process goes until the potential difference stops this migration from one metal to the other. But by that time, you have a battery, the potential from one side to the other side. It's quite ancient, actually, if you check. This is 180 years old stuff, and when the half century. And now we rediscover, and we have these electric cars and so on. It's very nice. I not really believe them because you can use lithium. It's a very rare metal. You can use carbon and everything, but still these batteries are big. So, for example, for the Apollo mission, they tried not to use batteries. They use fuel cells. They have hydrogen and oxygen, and they burn it, but slowly. So there was a chemical process, and that gave the electricity. In Apollo 13, it was exploded. In your body, also, there is a burn. The carbon and the oxygen are burned, but very, very slowly, and you use that energy. So I think it would be better to use fuel cells or something like this in cars. But there are other problems. I talk about the hydrogen, how interesting material is it. The hydrogen very, very slowly enters the metals, any metal, and makes them rigid. And then, after a while, it's a very short time, you have to change the tank when there is a catastrophe. It's not related to this, but the amalgam is forbidden in airplanes. I have seen randomly YouTube showed me experiment when you have amalgam and add to copper, to aluminium and everything, and the ore that is made is something weak and expanding, and the original metal is very destroyed. It's not the same with the hydrogen, but something similar. Doesn't matter what it is. So you know there are one metal with energy nivels where its electron are. There is another higher energy nivels. Its electrons are there. There is a touch. There is a you put them together, bonding them, and then from the higher level nivels, the electrons move to the other. Because they moved quickly, there is some missing electrons, positive charge on the higher level metal, and there is some negative extra charges on the lower levels, and this process goes until the potential that's built up stops the electrons, and that's the battery. That's the volt of Coulomb, and this is our battery. All batteries everywhere. It can continue copper, zinc, carbon, lithium. That's the idea, actually. There are rechargeable batteries. It's a different thing, but it's mostly chemistry. But this is the physics. And see, this is quantum mechanics. Volta made many experiments and made a series of contact potentials: aluminium, zinc, carbon. Oh, sorry, my pronunciation. okay, this is not, well, according to Duolingo, I have C1, but I think always tin, great. Tin, bismuth, iron, copper, silver, gold, platinum, and carbon. And this is the voltage contact potential series. And these conductors are named type 1 conductors. There will be other conductors very soon. There are some funny, I guess interesting features of these metals. You have two metals with a contact potential, metal number 1, metal number 2. If you take from this series, this volta series, another metal which has a potential between the first and the second, then the overall, the total, the sum of the potential difference will not change at all. This is one rule, one stuff. If you have a circuit from dissimilar conductors and the contact potentials are 0, then there won't be current here. That's another rule. It's quite interesting. More interesting stuff is coming. Yes. Some of them should be interesting. Actually, I don't know what background you have. So the physicists and engineers usually like physics and have some experience burning transistors and other stuff. I don't know whether you have or not. This is interesting. Okay, I just realized something. Okay, it's not possible. So you cannot see the title of this. The title is Peltier effect on transverse volleyball, and the thermoelectric effect. What it does mean? You have two different metals, and you add some thermal difference, or just thermal on them, some temperature, and then you experience current. You should know this. Gentlemen, can you book? There is this oven, the gas oven. And you burn the gas oven, and then the old way is there is a metal in it, and when you start the burning this gas stuff, then it bends. But the more sophisticated way is that there is a thermal battery, so it's Hungarian, thermal battery in them, two different metals, and give some electricity, and that electricity keeps a valve open. If, because of wind or anything or malfunction, the gas is gas is closed, is off, then there is no burn, then the thermal battery will not work, and the valve is closed. You can remove this, and if you remove this, then it's a good way to explode the full house. Because the gas and the air makes an explosive material. It's very good actually, very effective. It's called thermobaric bomb, and the thermobaric bomb is a good way. It's the biggest, the largest bomb which is not nuclear. It doesn't matter. I just wanted to explain you what is this stuff. You have two different material. You have difference in temperature, and then you got some electricity. It's called thermal battery, and the effect, the name of the effect is Seebeck effect. This is good. This is very well known. Have you ever heard about it? Not here, not in the university, in your life. You never cook? You use induced or electric oven or... No, never? Do you know boiler? Yes. It's the same. There is also a thermal battery in it. You never interested in how it works and anything? You know, this physics and mathematics is not to make your way to the diploma more difficult. It's useful. It is around us, everywhere. So when I walk, I see it everywhere. So physics and mathematics and chemistry and everything. So it's from daily life. We use it. Okay? That's the physics. No? It's interesting. No? For me, at least. But it's really daily life, and when you learn, when you're learning, you're studying, you will use this. There is a big difference between someone who knows the background between a process or any work. Because if you can just learn protocols. I lived in Finland. They say the Finns are very good, their English is very good. However, the Finns has a very special, very interesting feature. They has a phobia to decisions. There is these dogs. That's Monday, Tuesday, in Finnish, maanantai, tiistai, keskiviikko, blah, blah, blah. It is a joke here. But in Finland, if you don't have this type of joke, then Finn cannot decide which joke is, and then they find the skeleton after the cats. I'm joking, but not fully. So they really don't like decisions. The doctors learn protocols. If you go to the hospital, I was there unfortunately once, there is always a different doctor and they follow the same protocols. So you cannot bribe them like you could do it, you could have done it in Hungary. Now it's you can't, of course, but they do the same. But if there is a problem, many of them, 90% of them, cannot do anything. This is actually a mental state of mind because they're clever and know the background. But it's the same everywhere. So if you something went wrong, for example, in your computer, that you have to click here, and you don't understand why you will do it. And there is a problem, some misconfiguration, and there is a problem. Very more simple example. One nurse, an assistant doctor, used a program years ago, and they changed her monitor. So the window of the application was too large, it was out of the window, and it was frozen, and she could not do That's why we talk about the background. When you have something unexpected, something new, then you can handle it. Okay, here, thermoelectric effect and batteries. Now, something very, very interesting will happen. Okay, application, thermomagnet. Thermomagnet is in boilers, in these ovens, and other stuff. Thermobattery, that's the second. And I have no clue what is thermos actually, but I wrote it. I will check this out and that's an explanation. Peltier effect, not this is interesting, but the opposite of the Peltier effect. You have metals, you put them together, and you flow electricity, current between it. Then you experience no, actually not the opposite. So this is the opposite of the thermoelectric event. If you have two metals, you have currents. Then, depending on the potential of the metals, depending on the currents, you can heat the contact region or cool it. You have a cooler. A fridge is nice. Okay. You know how the fridge works. It's a carving machine. What is at least one disadvantage of a classic fridge? You know the carving machine. There's a compressor, some material, and everything. What's the problem with it? The main problem. You are engineers. What is the main problem? The possible source of an error. The moving parts, the compressor. After a while, it will degrade and you have to change it. But with this Peltier effect, or Peltier battery, you can cool stuff without moving. There is another way. Einstein and someone else did a fridge with magnets. It is used in nuclear submarines actually nowadays, and it cools the core of the nuclear reactor. And the cooling material is not water, but it's something sodium chloride or something sodium salt or something like this. Doesn't matter. This is very good, for example, to cool CCDs. Do you know what is CCD? Who has CCD in her or his pocket? Everyone has used general and special relativity theory with this instrument, the cell phone, the GPS. And you take photos. Yes, the photos.
Yes, and it is like a place in my phone where the photos, videos, and it's storage.
Yes, not the storage. That's also related to this, but I'm talking about the common CCD. Charge coupled device. You don't know it? Never seen it? Never heard it? You use a cell phone and you don't understand how it works?
It's like the battery in the phone?
Sort of. Originally, with cameras, you have just emulsion and photo emulsion, and you have this camera. Then you had what is the name? It was very expensive electromultiplying device, and then CCD. You never heard about CCD. It's better than one more. never seen this. It's very difficult how it works. This CCD is a frame, or actually a couple of pixels. All pixel is one detector. It's called charge coupled device. There is a way how it works and standardized. Your CCD, your cell phone, and also in my cell phone and in cameras, working well in this temperature. But very sensitive CCDs, for example, really good infrared cameras, need cooling. You can cool with nitrogen, you can cool it with, I don't know, air or whatever. But it's moving, and if you use this, then there is some humidity and also some ice on it, and the first one used them. But later they use this Peltier effect, and using this cooling battery, they use the CCD with this. Sorry, so I try to explain the Peltier effect with someone that you don't know, but I thought you know what is CCD. It doesn't matter. Okay, what we have, there is a constant, there is a temperature, and you can get the heat that is transported with multiplying them. I don't know whether I will give you exercise. Yes, this is it. You can cool with the Peltier. It's cool. Really cool, and both meanings of this word. Okay, that's also interesting. The melting property of the materials. Well, you have actually small magnets in the material, the atoms. The electrons are rotating around the core, and they are moving, so there are currents. The currents creates electricity. Very nice. The problem is that if you calculate this, then you will not get the right amounts for magneticity. It doesn't matter, it's first approach is good. So the materials has normative features. You know the electric stuff? Electrostatic features of the materials? You know? You? Anyone? Your clothes, for example, made from plastic or nylon or artificial material. If you remove, then you feel it. But also, the materials have magnetic feature. It's related both of them. It's very difficult, and I will return for this later. There is some quantity that is defined as magnetic moment, but I told you this is not good. There is magnetism in the vehicle, but we are here in the real world. There is air, there is liquid, there is a solid state. So the magnetic field and also the magnetism changing in the materials, because the material interacts with the magnetic field. You have to describe it somehow. There is a multi-permeability, this is this mu1, and there is another stuff, another constant that you multiply the stuff described in magnetic fields. But now here I stop with this because not this is important. Yes. There are different ways of magnetism of the material: diamagnetism, paramagnetism, ferromagnetism. The diamagnetism means it's induced magnetism. If you have oil which has very, very low carbon content, the Hungarian term is soft oil. There is no carbon in it, then it's not so rigid. Actually, you cannot jam it and you cannot compress it with your hands, but it's, then you cannot magnetize it. You can magnetize it with a magnet or an electromagnet or something like this. The magnetism lives and stays and exists until the magnetism, the outside of the material exists. There are paramagnetism, that's small, not really magnetized stuff. And the ferromagnetism is that you know as magnet. Do you like geology? Have you been in Iceland? Iceland? No? Iceland. Wait a minute. Do you know what is in Iceland? Why is that island is important? Or I ask, do you know what are tectonic plates? Apologize for everyone. So these are the continents, not the nicest. All continents are, so the inside, the core, the inside of the earth is liquid. Not very liquid, but high temperature and not solid. It's a very viscous liquid, so the viscosity is very high. There are solid plates on the top, where we are standing, and these are moving. Have you ever heard about it? Okay, great. It's a new theory, less than 100 years old, and when someone told this, then everyone thought the guy is crazy. What is here? Here is Iceland, and Iceland is on a separator of the American and the European plate. There are volcanoes, actually a lot of materials, and these plates are separated. If you go to Iceland, you can stand to the American and the European continent with your legs. New material comes from the inside of the earth. So there are layers here. You can do a lot of things with these layers. For example, determine its age, but which is important, the paramagnetic materials has a critical temperature. When you reach that critical temperature, then it loses its magnetism. But in the opposite side, if you have a liquid and it's cooling down below the critical magnetism temperature, it has some magnetism. The Earth magnetic field is changing. I mean, upside down sometimes, but it's really changing. So it goes to, I don't know, to Siberia, then Canada, and also moving on the Antarctic. So the direction of the north, magnetic north, or magnetic south, changes. So one proof of this crazy theory was that in these new materials, the newly magnetized material came and the magnetic field was frozen in them. The magnetic field changes. So, at the time when it became a solid material, then the magnetic field froze in it. So you can determine the direction. And on both sides of this ridge, actually, Iceland and in this north and south of the ridge, the paramagnetism of the rocks are in the same direction on the opposite side, symmetrically for this ridge, because their age is the same and they was made in the same time. Okay, doesn't matter. Sorry. I will explain this stuff later. It's not so simple to change the magnetism of the material. If you change the temperature, the magnetic field and everything, and then you do the same, the magnetism will not follow the same path. It's called hysteresis. I will explain you later what's this. I mean next time. Okay. Diamagnetism, paramagnetism, ferromagnetism. Magnetostriction. Have you ever heard about magnetic striction? Because I never heard this term before yesterday, but I experienced it many times. If you go to a transformator, there is high voltage. Also, if you go to a power electric current with 100,000 voltage, and there is no wind and it's quiet, you also can hear some voice. The current goes, the electricity, and changes the volume of the material. I will explain why later. And this is big. And this changes makes power waves, pressure waves. Orbit, its maiden name is sound. So the changing of magnetism changes the volume of the material, the conductor, and it makes sounds. That's the magnetostriction. Interesting. At high voltage, transformators and electrical, long distance electric transportation systems, you can hear this. Can you record this? Next time when you see a long time electric transportation system, then go there and listen. You will hear over. Just don't climb it because that's, yeah. Actually, some guys go there by helicopter, but they go very high salary. So yeah, actually it could be a career purpose if you don't have you don't afraid weakness and highness and okay, doesn't matter. Which is interesting. I talk about. Actually, to me, interesting, I talked about ferromagnetism. But also there is ferroelectricity. The materials has electricity inside. It means some polarization in the material. Okay? Now some familiar stuff. Have you heard about piezo electricity? Does anyone smoke here? No smoker? No smoke. It's great actually. Do you know how the lighter works? The lighter. There is a crystal, there is something metal, and it gives you electricity. You compress the material and it gives electricity. That's I cannot read it. Oh, and I cannot change the direction. Or what I have. I don't have. It's too high. Cannot climb there. Doesn't matter. At least I dare not. So this is piezoelectricity. You have a special material. Actually, there are in all material you have, but in special material the depth is higher. You put pressure on the material and you got electricity. This guy. Sorry. Spark, sorry. Spark. Apologize. Yeah, I need more coffee. Wait. That's better than the presentation stuff. You can read now. That's why there was no problem before it, because I didn't use this presentation stuff. So piezoelectricity, that's the name. It's also a name of the Italian guy actually. And you put pressure, hit a material, or just twist it, and you got spark, electricity. It's very good, lights, ignition, an engine or anything. Also, you don't, there is some moving part, it doesn't matter. There is the opposite. You charge the material and it's deformed. I think the electromagnetic waves are better, but this is also not bad. For example, if you have a detector and you are looking for charging electricity, you are in a top of a building and you are waiting for a storm, or you are in a mine, and there are always some methane in the air, and you don't like the electricity, then a detector can use this air restriction stuff. Okay, this will be a full presentation. Sorry, I will include it, but that was too difficult to process. LCD. You know it very well because it is in your cell phone. It is in your monitor nowadays. I had old monitors, old television that was big, and then we changed for LCD. Oh, this desk is so huge. What is it? There are crystals, lipids, and they are lipids. But if you add some electricity, then they are ordered and they change. The transparency change, the color change, everything changes. That's the liquid crystals, and there are many stuff, screens and displays which are based on them. The very primitive, the first one were in this displays of clock and everything, but we are far beyond this. I will return for this. Later. There are many types. And this is the different structures. And this is Hungarian, sorry. Yeah, and this is the monitor in Hungarian also. Sorry, so I have no time to process this. But something revolutionary comes right now. I'm pretty sure you have never heard about this. Do you know, have you ever heard about superconductivity? This is very cool stuff. You can, well, in the old days when I was young, we thought we will have this non-magnetic levitation trains and everything, but now we just have particle accelerators and some other stuff that's based on this. What is it? If you you take a material on one. Mercury, not amalgam, mercury. Yeah, so my memory is not perfect. You take mercury or some other material, and of course, its conductivity is higher and higher if the temperature is lower and lower. But if you can reach the absolute zero Kelvin, that's minus 273.16 Celsius, that's the zero Kelvin, you are close. And very interesting things can happen. The conductivity become infinity. Because the resistivity of the material becomes zero. Literally zero, not very close, it's really zero. It's called superconductivity. One interesting thing of this is the temperature, the critical temperature. If you reach it, then the material became superconductive. You put some electricity in it, and the electricity remains there, current, for 1,000 years. There is no resistance. So there is no resistance. It's a very interesting thing. There could be current, you can make very effective, low cost, and very strong magnets. It's good for tokamaks, 10 nuclear reactors. I will talk about them next time after the holiday break. And it's good for magnets, for example, particular accelerators in cell when my colleagues work. It's a good thing. Yes, these metals, for example, the mercury, called type 1 superconductors, and if you have this desirable feature at minus 27 Celsius, what do you desire? To do it in room temperature. Because which is the highest problem of Hungary and all electricity production. You cannot store the electricity. There is a nuclear power plant, there is a solar panel, there is a wind power station, there is a cool station, there is a gas station. They produce energy, and then you have to consume it. You cannot store it. There are lower effective alternatives. For example, these two-phase plants when you have a pool somewhere and a pool on the top, and when you have cheap electricity, then move water from the bottom of the hill to the top of the hill, and in the rush hours or in the top consumption period, then you just let the water flow and then you have extra electricity. But you cannot store electricity actually, energy. In Hungary, we have very rare situation for the last 5 years. Lot of solar panels were made. So during the day, in summer, we have a lot of energy, many energy. And in the old days, we did not need air conditioning, AC. That's why it is not effective. In the United States, everything is effective AC. In the United States, this would be unhabitable without AC. Most of them. It's tropical countries, subtropical country mostly, and desert country, most of the country. And so the ACs are working, the solar panels are working, and then suddenly the sunset comes and the sun disappears. The consumption is high, but the solar panels are disappearing, so then there is a big need of electricity. But during the day, because of the solar panels, the solar panels are consuming a lot of energy, and there were very strange situations for days when the stock, electricity stock, they pay if you consume the energy. Because the solar panel, you cannot switch it off, but you have extra energy, someone must be take it. So not the consumer paid for the electricity, but the power plant paid for the consumer to take the electricity. Okay, doesn't matter. So you cannot store the electricity, but with this you can do it. With metals, you cannot leave this minus 226 stuff, but if you have this called type first superconductivity, if you have some ceramics, then you can do it. But this is rare, very rare. The ceramics are not conductors, but they could be superconductors. For example, I have seen ceramics, superconducting ceramics, it's type 2 superconductivity. When we didn't need helium, just liquid helium, just liquid nitrogen to cool at minus 50 minus 60 Celsius, minus 160 Celsius is the temperature of the liquid nitrogen. Have you ever seen nitrogen? You haven't played with it? It's funny. You can throw your hand and nothing happens. It's not burned. If you put in your palm and keep it, then it burns. And if you put here, for example, then it forms tears and runs everywhere like water on the surface of the oven or what is it? On a hot metal. It's the same because it's boiling at this temperature. So you have this superconductivity, and let's see some superconductivity feature which is really desirable and really interesting. Okay, sorry for the Hungarian text. This is about the critical temperature, and also it is very sensitive for the amount of current electricity that you lead through. It's not important. Here are some metals like lead, lanthan, mercury, aluminium, zinc, uranium, and these are the critical temperature of them. You know, this temperature can be reached by liquid helium, and on the Earth, the helium was quite rare and very expensive. That's why they use hydrogen for balloons and everything. That's why the Hindenburg exploded long time ago, doesn't matter. But it is very expensive. These were very expensive. When they could switch to liquid nitrogen, we are surrounded nitrogen, it is in the air, then it was much cheaper. Okay, I have explained this to you. The type 1 and 2 superconductors. And the first are metals, and the others, not alloys actually, they are ceramics. High temperature superconductivity. Look, liquid nitrogen, 77 Kelvin, it's something minus 190, 200 Celsius, it's higher. But now we are close, so we are at, I don't know, minus 100, minus 50, 50 Celsius. And now, something, oh, I forgot. Sorry for this black stuff, it is the same. I will draw this on the board. That's interesting. This Meissner-Oxenfeld effect. So the superconductive material expelled drops out the magnetic field from inside of the material. When you are that's the material, and when the temperature is higher than the critical temperature, this is this black stuff, I will improve it, then the magnetic field just go through the material. When the temperature is lower than the critical temperature, then you can see this. The magnetic field cannot enter to the material. This is this black stuff, the black image. Sorry for this. What it does mean? Check this out. There is a superconductive material, that's something ceramic, there, and the black stuff is a magnet. You throw a magnet above a superconductive material, and it levitates. Because the magnetic field cannot enter the material, and that's it. So it cannot drop. And it's strong. So you can do this with in the opposite. You have something metal. You have a train, for example, with superconductive, I don't know, legs or something, and it levitates. And you can go through quickly, very fast, a few hundred kilometers per hour. The problem is that this is expensive, and which is cheaper, defeats in the economy the much nicer idea. One example with materials, there is no maglev, magnetic levitation. There are some in China, and also the Shinkansen, that's also magnetic, it's in Japan. But the French and the Germans developed the TGV and the Intercity Express. Why? Because they use common parts. And if the TGV train is not on a TGV place, then it can go. A magnetic levitated train cannot leave the path. So you need dedicated railway, you need a dedicated train, but for the TGV you don't need. So that's how the cheap stuff and more commonly used stuff defeated the nice idea of magnetic levitation. There is another example, the Intel processors. There were many other architectures, but I think that you don't learn nothing just Intel. Perhaps you know the Raspberry Pi, some of you know the Apple, now they use different architecture. These are much better than Intel, but the Intel is cheaper. Doesn't matter, it's not related to this stuff, but which is interesting. You have high temperature superconducting material, it excludes magnetic field, so if you drop a magnet, it levitates. That's nice, actually. Beautiful. I have seen this experiment a long time ago. Okay. The theory of this, Wolf Nobel Prize. I talked about photons. The photons are the particles of the light. If you check the oscillating atoms, then those waves could be also quantitative, and we call them phonons, not photons, phonons. And this is the main obstacle of electrons in the material. In superconductivity, a very interesting thing will happen. The electrons, single electrons, become coupled with different spin, and they made pairs. It's called Cooper pairs. These Cooper pairs has a spin that is 1 and not a half. The half spin and the multiplication of half spin particles are called fermions, and the Fermi direct statistic is applied for them. The Bose-Einstein statistic that you have never heard before are applied, as I mentioned, applied for bosons, those particles which has the spin, it's integer spin, 0, -1, -2, -3, whatever you want. The two electrons, the pair, the Cooper pair, forms a boson actually, a virtual boson. They are not stable, so they change, it's like couples in real life, they are change, come together, they change the partner, doesn't matter, it's okay? And they could work like boson waves in the material between the bosons. And with this tube effect, how they can cross high potentials. And this happens in superconductivity, this Cooper pair forms, and the normal way of moving an electron is just moving and then collapsing, not collapsing, colliding with the phonons, with the ions and everything. If you have these Cooper pairs, then with tube effect, you go through everything. And that's the superconductivity. The theory is more difficult actually, and it was Nobel Prize. Nowadays, so it was something a few decades ago. Yes. End of the lecture and end of my talk. Thank you very much. I will return for some stuff. So I suggest have a short break and then we can continue with calculation. Thank you very much.